Hello and welcome back to Teach Me in 10. In this episode we'll be hearing from Ken, who's a Principal Application Scientist at PerkinElmer. So without further ado, let's get into the video.
Thank you for the introduction. My name is Ken Neubauer and I'm an Application Scientist with PerkinElmer. Today I'll be talking about the analysis of additives in lithium-ion battery cathode materials using ICP-OES. Lithium-ion batteries are becoming increasingly popular, powering everything from small electronics up to electric cars and other electric vehicles. The increasing growth and demand for lithium-ion batteries, development is continuing to improve their performance. Four major components of lithium-ion batteries are the cathode, the anode, the electrolyte, and the separator. The cathode serves as a source of lithium ions and determines the energy density of the battery. The anode stores and releases lithium ions, while the electrolyte allows only lithium ions to move between the anode and the cathode. The separator prevents the flow of electrons between the anode and the cathode and allows only selective passage of the ions. As we can see, there are examples of materials for each of these components. If we look schematically at the battery, we can see what it looks like here. While battery is discharging or releasing power, electrons are flowing from the anode to the cathode through the electrolyte and through the separator. When the battery is charging, the lithium ions are flowing back from the cathode to the anode. What we'll be talking about today are additives to the cathode materials. So the part of the battery is represented in blue. So looking at additives a bit more closely, they're added to cathodes to enhance the performance. Because the performance of the battery depends on these additives, the accurate addition and measurement is critical. They have to be added at the exact right proportion and therefore have to be characterized and measured accurately. Some common additives include aluminum, boron, magnesium, titanium, tungsten, and zirconium, as well as others. These are usually added at fairly high concentrations, usually above 1,000 milligrams per kilogram. But analyzing these additives is challenging because the high matrix can cause signal suppression. While it's possible to dilute out these effects using large dilutions, every time we do a dilution, it introduces a source of error. Therefore, that could possibly compromise the analysis. Again, it's critical that these additives are added in the correct proportion. Therefore, they must be measured very accurately and very consistently. To perform these analyses, ICP Optical Emission Spectroscopy, or ICP-OES, is a preferred analytical technique for a few reasons. First of all, it's a very robust technique which is able to handle high levels of dissolved solids or difficult matrices, such as these dissolved cathode materials. Also, we can measure high concentrations accurately with minimal dilution. Again, there's always going to be a little bit of dilution necessary in preparing a sample, but you want to minimize the amount of dilution. And also, ICP-OES is versatile, as we'll see. So the goal of this work is the accurate determination of aluminum, boron, and zirconium additives in NCM622, which is a common cathode material. So let's talk a little bit about ICP-OES. Basically, the way it works is that a liquid sample is pumped to a nebulizer and converted to an aerosol. So these cathode materials are solid, so they first have to be dissolved and converted into a liquid. The aerosol enters the ICP, where the atoms are excited and emit light, as we see in this photo of a plasma on the right. Each element emits a light at its characteristic wavelengths, and the light is sorted by a spectrometer and detected. The intensity of the light corresponds to the amount of the element present. So now let's look more at the samples and the sample preparation. So our samples is an NCM622 cathode. This cathode material contains lithium, nickel, cobalt, and manganese. To that, additives aluminum, boron, and zirconium have been added at the concentration shown in the right-hand column. The sample preparation involves taking 0.3 grams of the NCM622 and adding it to 8 mL of aqua regia. The vials are then capped and heated at 150 degrees for 1 hour in a graphite digestion block. The sample is then cooled to room temperature and diluted to 30 milliliters with deionized water. For analysis, the sample is diluted an extra 3 times for a total of 100x dilution. When we perform the quantitative measurements, we want to calibrate, and we have calibrations at 2 different levels. Aluminum and zirconium are calibrated at 10, 30, and 50 milligrams per liter, while boron is 0.3, 3, and 10 milligrams per liter. For the utmost accuracy, we want to calibrate right around the expected concentrations. This will always provide more accurate results than using just a general calibration. Again, the concentration is added is critical, so we want to make sure we get the accurate results. We perform these analyses on an Avio 550 Max ICP-OES using a standard sample introduction system, as well as normal plasma conditions. We use auto-integration as well as a read time of 5 seconds. Now what we could do, we could also go to longer read times. Longer read times will provide more accurate results, more precise results. However, we also want to balance accuracy with sample throughput. Some of these labs that are doing these analyses, they're high throughput labs, and they offer many types of, they have to analyze many types of battery materials. So we showed the 4 different components. They can be analyzing many different types. So we want to have the best compromise between speed and accuracy. And for that, we chose a read time of 5 seconds. The auto integration automatically determines the optimal integration time based on the pre-shock. And here are the wavelengths we use in the plasma views. We analyze aluminum and zirconium with a radioplasma view and boron with an axioplasma view. In addition, we also looked at scandium and yttrium. These are used as internal standards, and we evaluated both of them as they are commonly used internal standards for ICP-OES. Now, the reason we use 2 different plasma views is that each provides something different. Radio view, it'll minimize matrix effects and increase precision, and it's good for higher level elements. In this case, the aluminum and zirconium were present at higher levels than the boron. However, axial view, it will increase sensitivity for low-level elements. And if we have low-intensity elements, we get higher sensitivity, will increase the precision. In this case, boron, while it wasn't present at low levels, the line we chose is not the most sensitive line for boron. And we chose these wavelengths to avoid interferences. So by using axial view, by using dual view, we could pick the appropriate wavelengths. Okay, so now let's take a look at the results, which are shown in the plots on the right. If we look at the first plot, using scandium as internal standard, we see that both aluminum and boron recovered within 1% of the true values, so it shows we have high accuracy. However, zirconium recovered a little bit lower, at only 94%. We took this data and reprocessed it with yttrium as internal standard, and we saw a similar trend. Aluminum was still 99%, boron decreased a little bit, and zirconium went down a little bit. So this shows that scandium is actually a better internal standard for this analysis. It's actually not necessarily a bad thing because yttrium is sometimes used as an additive. So if we're trying to develop kind of a generalized method for how to do analytes and cathodes, additives and cathodes, scandium is a better internal standard. We're still puzzled why the zirconium was recovering lower consistently. So to kind of rule out matrix effects, we diluted the sample another 3x, so for a total of 300 times dilution, as we see in the plot at the far right. And to see the results basically were unchanged. We're still recovering a little bit lower with zirconium. And we were a little puzzled. We talked to the manufacturer of this cathode material, and they told us that zirconium was added as zirconium dioxide. And this turned out to be the problem, because zirconium dioxide is insoluble in aqua regia. Therefore, in order to get the recoveries, what we have to do is we must shake the sample just prior to analysis to prevent this, or to limit the amount of zirconium settling out from solution. Now, it is possible to digest zirconium dioxide. However, we'd have to use hydrofluoric acid. This is not always something that's really easy to do. First, hydrofluoric acid can be very dangerous to people. The other thing is that we have to change our sample introduction components. We have to use a spray chamber and a nebulizer that are resistant to HF. HF dissolves glass. The most common sample introduction components are made of glass, so nebulizer, spray chamber are made out of glass. If we try to analyze hydrofluoric acid solutions, we'll dissolve them. So we have to use a non-glass spray chamber and nebulizer. These are available and can be used, but again, given the dangers of HF, most labs prefer to stay away from it if possible. So we show that we get acceptable results for zirconium just by agitating and shaking. To summarize, we've seen that ICP-OES can be used to successfully measure additives and cathodes using lithium-ion batteries. In this example, using NCM 622, aluminum and boron recover within 1% of their true values, while zirconium recovered within 5% of its true value due to the nature of the zirconium dioxide additive. We've seen that the dual view capability of ICP-OES allows for flexibility and increased accuracy. Radial view can minimize matrix effects for higher level analytes, while axial view provides higher sensitivity for low level or less sensitive analytes. More details about this analysis can be found in our application note, which is shown on the right. With that, I'd like to conclude, and thank you for your time. I hope you found this helpful.
Thanks so much for watching this episode of Teach Me in 10, and I hope we'll see you again very soon.